all for coming. So this is going to be my third presentation on the lunar initiatives, returning to the moon for all mankind. So the first evening at our vendors, investors, partners, and presenters meeting, I gave a general overview of the whole thing. I'll go through a little bit of the beginning just to set the context again, but today I'm going to focus on the challenges and incubators, which are 2 of the 5 initiatives in the Lunar Cubes initiative. To begin with, what's the purpose of the initiative? Why did we create this? Why did we create these workshops? The workshops are 1 of the 5. So our purpose in creating the initiatives is to engage the best and the brightest from all over planet Earth in addressing the most profound questions ever asked by humanity about our place in the universe and our expansion into it. In so doing, we'll develop and prove new 21st century technologies that are only just now being imagined, and through their commercialization bring new value and hope to all mankind. Already in this workshop, I think we've heard of quite a few new technologies that are becoming imagined and are becoming real. I'm very pleased to hear we have in our audience yet another Google X Prize team, and they're making strong progress too. So we've heard from 3 Google X Prize teams. They all have tens of clients and customers. They all are making progress. They all are going to make their attempts, but they're certainly going to fly. And it's quite exciting. One of the core themes that allowed us to go from just the workshops and just looking at lunar cubes is this idea of the new cosmology, where in the 20th century, cosmology was all about stars and galaxy and how big the universe is. With the latest discoveries from Kepler and other missions, we now know there are more planets in the universe than there are stars. If you really want to understand the universe and how it works and why we're here, you need to be studying planets, not just stars. And we also now know that there are many habitable terrains in our own solar system that represent excellent analogs for other planetary systems and life in the universe. And so one of the things our workshops and all of the aspects of the lunar initiatives are intended to bring out is this flexible path to life in the universe. We need to look to find life on Mars. There could be life on Europa and Enceladus. We know there are habitable terrains. The most bizarre and interesting one is there's possibly life on Titan and Triton. In these cryogenic environments, there are things that look a lot like life in the early data we got back from a couple of missions. Where does the moon play in all this? How is the moon the gateway to the entire universe? The moon is San Francisco in 1949 or 1849. All the gold rush guys went to California to go find gold in the mountains, but they all started in San Francisco. They all bought their shovels and their mules and their blue jeans in San Francisco. So if you want to make money in space, you want to be founding a city in space, the moon is the place. That's where the resources and their ISRU is going to happen. That's where scientists are going to study analogs, scientists and engineers, analogs to systems that are farther away and more expensive to get to, and we'll be doing our training and learning how to live out there. Another thing we've heard a lot more about, as I just said, I've now heard from 3 Google X teams who are absolutely planning on going to the moon and absolutely believe they have a lot more than 1 flight in them. Chang'e 3 will be landing within weeks, and so the Chinese will have a large rover on the moon by Christmas. The Russians have 4 landers and an orbiter in plan for over the next 5 to 7 years. Even NASA's going back to the moon. LRO, the Lunar Reconnaissance Orbiter, will be there for another decade or more. The Resolve mission is going to fly in 2018. SLS, the Space Launch System, has recently announced that they're going to be hosting 12 6-unit lunar cubes on their test flight. Korea has an orbiter. The moon's going to be a very busy place. And so it was putting those themes together, I said, this is a lot more than a couple of workshops. So we created the lunar initiatives and the lunar workshops. So there's 3 workshops: lunar cubes, lunar superconductor applications, and lunar scientific opportunities in cislunar space is our newest one. We're going to create special interest groups where people can get together and talk about these things not just once a year, but every month. We heard some topics earlier about things that need a lot more further discussion, not the least of which is the legal issues. So we have the special interest groups. Today I'm going to talk about the lunar challenges and the lunar incubators. And then the other initiative is called the Lunar Geophysical Year. From the previous chart, we can see the moon's going to be a very busy place in 2018. And we heard a lot about the political and legal challenges associated with communication radio. There's absolutely going to have to be international, political, very high-level discussions came out of the original geophysical year in 1958. In 1958, they launched Sputnik, they discovered the Van Allen belts, and most importantly, from this point of view, they also created the Antarctic Treaty System, which is one of the most successful treaty systems out there. We're going to need something similar to the moon, and we're going to need it soon. So as part of the lunar initiatives, we're going to begin talking to people about the political issues as well as scientific and engineering issues. So the lunar workshops, I've discussed those. The SIGs, every workshop will have 2 to 4 special interest groups associated with it over the course of next year. We're going to launch 5 or 6 of them this December and get them up and running, and then we'll start adding others as we get more volunteers to run them and more clarity on what people want to talk about. And then, so basically a special interest group is a monthly webinar, people trying to write joint papers, trying to write joint proposals, and then they will present at all the workshops. The IGY, I talked about that. The original IGY was in 1958. They've got the space race started. The 60th anniversary will be 2017, 2018. And as I mentioned, the moon's going to be a very crowded place by then. And so we're going to want to have that international community talking amongst themselves about how are we going to make sense of all that. So that brings us to the Lunar Challenges. And so the Lunar Challenges are like the Google X Prize. As part of our workshop series, as part of a variety of things we're going to do, is we're going to try and create at least 1 and probably 2 or more challenges, big prize challenges. Eventually, I think we'll be able to have $1 million prizes. Next year and the year after, they'll probably start off a little smaller than that. But one of the ways that we're going to be doing that is I figured out a clever way to create that. The way you create your big prize, the way you raise that $1 million is you don't have to be NASA, who has $1 million or used to have $1 million. You go out and you crowdsource it. You say, we'd like to give a prize to somebody who builds a really cool lunar cube. You go to Kickstarter or something and you start raising awareness, getting interest. You sell them a T-shirt. They give you $100 and they get a T-shirt. They get their name engraved in the lunar cube when it launches. And maybe in the first year you raise $250,000. You design the prize so it takes 2 or 3 years to win because that's what you want to do anyway. And every year the prize gets bigger and bigger and bigger. So it's like the lottery. The harder, more interesting, and more exciting the challenge is, the bigger the purse will become naturally. We'll use regular sponsor dollars to do the administrative and other kinds of promotional aspects. But basically, challenges are very critical to the success. One of the key features of the challenges, and Google X Prize is the perfect example. We talked about challenges in an earlier presentation, and there was a question of, well, is it really a good way of doing R&D? Can you really incentivize discovery through challenges? And look at the Google X Prize. They put up a $30 million prize. People have spent probably a few hundred millions of dollars by now. And we've already met 3 teams who are within striking distance of realistically at least trying to get to the moon. And I bet more than a few of them will succeed. So that's disruptive change. When the Google X Prize went up, I would assume anyone, including myself, would have told you that a private enterprise going to the moon, let alone 3 or 4 or 5 credible challengers, was just not in my imagination. And now it's truth. It's real. In another 3 years, we'll know who gets to go and who even wins. But challenges are a way of creating disruptive technology. It's a way of creating non-continuous improvement. So it's disruptive, it's discontinuous, and it's a kind of accelerant to progress that is hard to do in a regular research program. So what's an example? And so these are I'm going to show 2 notional challenges that we will put up. One of the things is the actual rules of the challenge by the time we launch it. Those rules will be defined in the workshops and through the special interest groups. So we have some of the top people in our workshops and some of the top people in our special interest groups. We're going to go spend 6 months or so coming up with a detailed set of rules of what a great challenge would really be and how you would actually run it as a fair competition. But an example of what one might look like is, let's take a MacBook Pro. The new MacBook Pro is brilliant. I dropped out of college in 1984 to try and create a cluster computer, and the new MacBook Pro is beyond my wildest imaginations even back then. And so the question is, can you take the new MacBook Pro and put it in a 1U format? Could you even do it, have it run at 40 Kelvin and say 10 watts of peak power? You want to give it a modern open source operating system so that you can do cluster computing at the moon. That's what the target is creating a a computer cluster out of CubeSats that you gang together and then fly into deep space. So I would imagine there are quite a few people who say, Apple just spent, I don't know, $1 billion making the MacBook Pro, and I don't even think anybody else can beat that. But I bet large sums of money, and I am, that if we put up $1 million prize, somebody could probably do it in 5 years, 6 years. I bet if we really put up $1 million prize, it gets done in 3. It's amazing what happens when you put up some money. And this is an electronics challenge. Those things always go fast and disruptively. Another one is high temperature superconductor. So HTS stands for high temperature superconductor. So an all cold high temperature superconductor flywheel, we already know of one small flywheel, superconductor flywheel, that fits almost in a 1U format. Wei-Kan Chu, one of our first partners, had a little demonstration model that he had built years ago, and it just happened to be about the size of a beer can, which just happens to be about the size that fits in a 1U cube. And he got very excited about the prospect of redesigning that as something that really does fit in a 1U cube, and then also something that is all cold. You don't just cool the superconductors, you cool the entire apparatus. So all of the electronics, all of the motors, all of the bearings and flywheels are operated at 40 Kelvin. So you would want to build one. It's got to fit in 1U. You want to be able to gang them together into an array. Because if you're running around at the bottom of Cabeus crater where it's between 20 and 40 Kelvin, the only batteries that you have any chance of working are going to be superconducting flywheels. You might be able to come up with some other, there's some nuclear processes, but not the ones that we've used before, so those will take 20 years to create, and maybe you could fly them, maybe you can't. But flywheels we know will work, and so this is a technology that from a physics point of view is guaranteed to work. From an engineering point of view, maybe we need a challenge, maybe we need $1 million prize to get that problem solved in 5 years instead of 20. So those are the challenges, and we'll do many more. So there'll be other ones. And then another type of challenge that I haven't mentioned yet is we'll do science challenges, which an example that people have brought up is, I think it's the Gold Coast Mining Company. It's a pretty common example where a gold mining company was unable to find gold in their own property, and they were going to go bankrupt in 5 years, 10 years at the most. And they had no clue as to where to find gold on the land they owned, and they didn't have the resources to go out and buy new land. So they did the completely heretical thing of putting all of their data essentially out on the internet, put up a $500,000 prize and says, the person who finds the most gold on our property wins $500,000. They transformed themselves. They went from a $100 million company to a $1 billion company, and found more gold than anyone ever imagined possible on the land they already owned with the data they already had. So we're going to do that with space science questions. The one that jumps into my mind is there's a very cool experiment on a lunar reconnaissance orbiter called LAMP. And it has these very intriguing images, and even after whatever it is, 4 years, nobody actually knows what they're imaging. They know it's real data because it matches up with where the craters are. But why some craters are dark and other craters right next to them that you would guess should be identical are light, nobody knows. And so it's very much like that. The guys who designed it, they know that it works, they know what the physics was when they built it, but nobody really understands what those images mean. I'd like to put up a $100,000 prize and see if somebody can figure that out. So let's talk about the incubators. So we're here in Silicon Valley, so incubators are the big hot thing. So a startup incubator is you take some college kids or some ex-NASA guys, and you try and build a business around them. You teach them how to run a business. You teach them how to be entrepreneurs. You teach them the skills that most scientists and engineers and inventors don't yet have. And then your goal is to make them investor ready and help them go raise capital and create a startup. So with each of our themes, we're considering creating incubators, because out of these workshops, out of our special interest groups, out of our challenges especially, there are clearly going to be investable technologies. A month ago, I wasn't sure I was going to tell anybody I was interested in creating an incubator. A couple of weeks ago, I decided, okay, I'm going to add it as One of the initial initiatives is to create incubators. And by the end of this week, I'm announcing right now today that we're going to actually start on 2 of them. The 3 that we're considering is, of course, a Lunar Cubes incubator to help people organize company around CubeSat ideas. But the 2 new ones that we're actually going to get started on are Lunar Access and Lunar Networks. And I'll talk about those right about now. How do we organize an incubator? What do I mean by an incubator? So as we create the incubator, one, it has this general structure that I designed, and you'll notice we're doing it with the workshops already. You create what's called a virtual institute, which is for us essentially the SIGs, the special interest groups. You take scientists and engineers from all around the world, and you get them talking to each other about the topic you think is interesting. So in this case, we'll use the SIGs that we're already creating to focus on this network of hardware that's going to be in orbit anyway, and see how we can commercialize that and utilize that. And in the network access, in the Lunar Access, we'll look at the different launch architectures and begin doing studies and papers and workshops and different kinds of activities on all of those things. And out of those, potentially startups will emerge. And as they emerge, you need to do 3 things. Startups need banking. Startups need very different types of banking services than a regular company. If you want to give a credit card to a startup, you better know what you're doing. Asset creation, collateralization. So again, very often a startup only lives 2 or 3 years before the team kind of goes their separate ways. But during that time, they've almost always created some sort of intellectual property that could live beyond them. If, again, you're going to create a successful incubator, you need to know how to capture that and collateralize it. You need to train the individuals. From there, we're going to create this virtual institute, an open source community for software, a maker community for hardware, and then eventually you start creating startups and skunkwork teams, because not everybody needs to be a startup. Some people can be skunkworks teams within entrepreneurial teams within bigger organizations, but they still need to know how to think like entrepreneurs, even if they're part of JPL or Boeing or a large university. So we'd be training those kinds of folks of how to think and act like entrepreneurs, no matter what environment they're actually in as a business. So what would this look like? So the Lunar Access Incubator is, just as we discovered there's the 3 Google X teams and several more beyond who might be going to the moon. Well, they've each got an architecture of how they think they're going to do it. So the Lunar Access Incubator is going to look at, I think I've got the wrong, okay, so ignore the stuff on the left. That goes to the next one. What we're doing is now we have the model architecture. So we have SpaceX wants to sell the Dragon Lab in low Earth orbit. Then we also have the Falcon Heavy. The MIT Halo project last summer talked about being able to send a crew of 3 to the moon with 2 Falcon Heavies and a Delta. So from that we looked at, well, what would happen if you have a Falcon Heavy and you assume you're going to use a slow cargo orbit? What can you do with that? If you've got to do a fast crew trajectory, what can you do on a Falcon Heavy with that? So we set these up. Astrobotic has their architecture. We know exactly what that looks like these days. Moon Express has their architecture. The other Google X Prize teams have proposed architecture. So in this incubator, we'll set up the special interest groups to start looking in doing studies of what would you put in a Dragon Lab? What would you put in a slow cargo vehicle? What is it suitable for? How would you load up that Astrobotic lander with as many different things as you can imagine? As those incubated ideas grow, you then may be in a position to create a company out of them. And when that happens, we'll have an investor pool ready to look at the projects as they come out. So now if we look at this one, the Lunar Networks Incubator, this is a project that came out of, we heard about DentSurf and the DTN a little earlier. Looking at that, looking at the DTN, the delay tolerant network idea came out of the experience on Mars. You had these Mars orbiters that were more or less done with their science life, or at least they had some spare capacity, and they began supporting the rovers and other orbiters and other different resources. They became shared amongst all of the Mars users. Well, we have the same thing in space. We have LRO right there. It's right there right now, and it's going to run out of most of its science funding in a year or two, but it can easily live another 10 or 11 years. How can you reuse and reutilize that asset? The Koreans are going to send up an orbiter. The Russians are going to send up an orbiter. So in approximately 2018, there are going to be 3 orbiters. How do we create a network out of those the same way we have a network of orbital assets at Mars. So that led to the obvious thing of shared communications, creating this network of communications. But what else can you share? We saw with the ULA presentation earlier this week, he was talking about a 100-watt power supply on a carrier to dispense CubeSats in lunar space or Mars space. Once that carrier gets where it's going and it dispenses its CubeSats, it's got a 100-watt power, 100 kilowatt, pardon me, 100 kilowatt, not watt, 100 kilowatt power supply for the ion motors. They currently can put together a 25 kilowatt, and he was thinking they could fit 100 kilowatts into their carrier. Once they dispense the CubeSats, they know that that power supply that is no longer needed, either once they dispense their payload or just when they get to where they're going. When they're not in motion, you don't need it. How could you share that asset? Because again, a power supply like that probably is going to live 5 years, 10 years. How could you share that power? And you can share it by beaming it to someone else, but you can also share it by, if you've got extra large computers, which you're probably going to have on a carrier like that, now somebody else can beam in and say, could you please spend 50 watts solving this math problem for me and send me the answer when you're done? So you don't necessarily have to literally beam the power to another resource, a rover or a lander or an orbiter, to effectively share the power supply amongst multiple users. So that's communication sharing is the obvious one, and the DTN work is well underway. I'm glad it's more advanced than I imagined. That's power sharing, compute sharing. Again, same sort of thing. You put extra large computers up there because they'll live for 5 or 10 years. They're orbiting in the moon somewhere or other. Then now you're doing cloud computing in lunar orbit. We also talked about the challenges of navigation. Most likely, these 4 themes assume that you have a robust node. It's an orbiter, it's a lander, but one way or the other, it's got more resources than the average lunar cube, certainly, or other users. So there are small rovers playing and talking to the big rover. And then so one of the other resources the larger, more competent nodes are probably going to have is much better knowledge of their location. So you may be able to cobble together some sort of navigation system out of the fact that you've got 10 spots in cislunar space where you know exactly where they are. Can you use them as some sort of relay network to give at least some sort of estimate of location to something as small as a 1U CubeSat wandering around with much fewer resources? So as I mentioned, with this, there are real assets that we can talk about. So again, we begin with a virtual institute to say, how would we do that? What is, pick up where DTN left off and move it forward. Start creating a DTN-like protocol for how would you beam and share power. How would you share your computer services? So there are a lot of algorithms and methodologies that we can begin working on just in the special interest groups about how you would utilize the 3 assets we already know are going to be there. It's the 3 orbiters I've listed here, and however many landers are on the surface of the moon, and some of those will start living through the lunar night and live for months, if not a year or 2. So I put down 2 possible startups that we might begin working with. One is called Tweets from Space. So that idea is you just relay a tweet, you bounce it off LRO or you bounce it off the astrobotic lander, and somebody might pay $1 for a tweet that bounced off the moon and came back. So that's that's just reusing spare bandwidth that isn't being used, and maybe you can make a business out of it. And then I call the gumsticks to clouds model. It's obviously gumsticks probably won't be the actual technology that does that, but if we can start sending up a couple of CPUs that do work inexpensively, and then start ganging them together, and how would you reuse them? How would you reuse the computer power? I mean, for example, LRO's got some pretty. It's got a bad communications system. It's it's slow upload and pretty good download. It's got a pretty big computer, and it's got really big disk space because of all those images. When they're not doing science, they might be able to do something else. And so that begins to look like cloud computing in cislunar space. And again, I suspect that Russian orbiter and that Korean orbiter are going to have pretty nice computer assets that could be shared with others as well. So again, in the context of the special interest groups, we'll just start asking the question openly, how could we utilize these assets that are already there? How could we augment them with what's next? So in keeping with collaboration accelerates exploration, what I need next is partners, participants, and sponsors. And so thank you all for being here. And there's some contact information here. There's on our website. We'll be communicating continuously from now on, and on the websites and through our own tweets and Facebook pages are all getting launched in December. So you will hear more from us than you want to. Thank you very much.